In this video, we are going to be looking at chapter 12, but instead of a dependent samples t-test, we're actually going to be extending the idea of a dependent groups design to when we have more than two levels. And this is what is known as conducting a repeated measures ANOVA. So while a dependent samples t-test looked like this, we had something like time point 1 and time point 2, where everybody served in both conditions. In a repeated measures ANOVA or in a one-way within subjects ANOVA, we have time 1, time 2, but now we start introducing 3 or more within subjects variables, where everyone serves in all of the conditions, so more than 2. So the main difference between what we refer to as a within subjects design and a between subjects design is a within subjects design, we have participants in different conditions that are related, or they are the same people. And this latter portion here, the same people, that is the most common. So for instance, a within subjects design could look something like this. Um, let's say you go in for an assessment of anxiety levels after 4 weeks, and then again after 8 weeks. And the doctor tracks whether your anxiety symptoms are decreasing over time. You are serving and giving a dependent variable value at each of those specific time points. And so we can see essentially whether there is an effect of time being our variable of interest. Now, there is an advantage of using within subjects designs, and we highlighted these specifically when we talked about the repeated measures t-test, also known as the dependent samples t-test. And the main advantage of within subjects designs are their reduction of error, specifically in our data. So because we are using the same people in each of our conditions or in all of our conditions, those individual characteristics and participant differences are held constant across those conditions, right? Now, when we extend this to a repeated measures ANOVA, this means that our error term in the F ratio is going to be lower, all things considered, if you're comparing a repeated measures ANOVA with a one-way between subjects ANOVA. And what happens when we lower that error term? Well, if you remember, the F ratio is just your variance between divided by the variance within. So if you lower this denominator, you're going to get a much larger F statistic. And the larger the F statistic, the further right it's going to be found in the distribution. The more likely it's going to be that we're going to reject the null. So the way that we're able to reduce this error is by pulling out variance that's associated with participants. If we have different participants in every single condition, there's going to be a lot of accumulated unsystematic error just by those kinds of individual characteristics. But if everyone's the exact same, we can actually pull a little bit of that error out, reducing this denominator term. So there are no between subjects differences that help to contribute to the variability in the data, specifically in these within subjects designs. Now, it's not all positive, right? There are some downsides to using a repeated measures design, and we highlighted a few of these when we talked about the dependent samples t-test. But one of the disadvantages is if the study procedures are long or difficult, this can result in fatigue effects or perhaps practice effects. So it's not that the task itself is getting more difficult. You're just getting tired of doing the task over and over again. So it may not be that certain types of interventions are actually leading to an increase or decrease in performance. It's just that either the task is boring, so you're doing poorly because the task itself is long and boring, or you're getting better because you're sitting there over and over and over again, taking the same kind of assessment. Other types of disadvantages could be things like carryover effects. So for instance, if we're testing 3 different brands of coffee, let's say brand number 1, 2, and 3, and I'm wanting to measure heart rate. Well, I can get your value for each of these cups of coffee, but I would want to make sure that I have enough time in between giving you these different conditions so that the caffeine in your system is able to leave your system. One other disadvantage that we typically need to think about is attrition. So attrition and participant dropout is a major issue with repeated measures designs. And so the reason why it kind of looks like this. So let's say that we have four different conditions, right? We have four different conditions in our experiment, and you give me a dependent variable value at time point 1, time point 2, time point 3, but then you just leave, right? You just leave. So you don't give me a fourth value. What happens to all this other data? Well, because you don't give me that fourth value, you actually can't be included in the analysis. So you lose all the other points associated with that person if they don't complete every single level of your variable. So this can be very problematic, right? Especially if you're doing a very long kind of study. So this is something that we have to keep in mind. Is there a rate of attrition that is high? Are we anticipating people leaving our specific study early, right? In the case of animal models, what happens if an animal dies in the middle of an experiment, right? What happens to its data? And possible bias can also come from the order. And we talked about this in chapter 12 with the dependent samples t-test, the order of the conditions that participants experience. Those order effects could be influencing the data and influencing the results. So one way that we can get around this is by counterbalancing. And remember that counterbalancing is where we are still having everybody experience the levels, but instead, they are going to be experiencing them in different orders, right? And so we can do Latin squares or full counterbalancing, right, in order to alleviate that problem. So when we talk about a repeated measures ANOVA, remember, an ANOVA is used when we have more than two groups. The repeated measures portion of this design is saying that we have more than two related groups, specifically. So the defining characteristic of a repeated measures ANOVA is that we have one group of individuals. Remember, they're all the same in every group. They participate in all of the different treatment conditions. So a repeated measures ANOVA is used to evaluate mean differences in two general research situations. So a study where the researcher manipulates an independent variable, where we create the 2+ conditions, where we have the same groups of individuals tested in every condition, or where we take the same group of people and we observe them at 2 or more, or rather 2+ different times. So time point 1, time point 2, time point 3. And while time is generally the most notable repeated measures variable, we can also do other types of just conditions, right? So if I want to do coffee brand 1, coffee brand 2, coffee brand 3, my independent variable is type of coffee, and I can have everybody try each of the coffees. That's still a repeated measures because everyone is contributing in each of the conditions. So the logic and the process is very similar when we're talking about comparing repeated measures and one-way ANOVAs. But it is slightly more complicated just because we are still looking at variance differences, but we are going to be able to take some of that variability that is due to individual differences. We're able to take that away, right? Because everyone is serving in every single condition. So the whole idea, though, in an ANOVA is we're still comparing the between group variance to the error variance. At the end of the day, we're still getting an F ratio, the variability between our groups, the variability within our groups. The only thing in a repeated measures ANOVA is we're going to work to decrease that error rate or that error term. So in a repeated measures ANOVA, we are able to pull out variance associated with the participants. And the goal of that is to lower our denominator value. So the primary advantage of the repeated measures ANOVA is the elimination of variability that's caused by those individual differences. Remember, individual differences are those things that are going to add to variability because people are just different between our groups. But in a repeated measures ANOVA, everyone is the same in all the groups. So we can actually take out some of this individual difference variability. So in statistical terms, we say that a repeated measures ANOVA test has more power. Because again, what happens when you decrease that denominator in the F ratio? When you decrease the denominator in the F ratio, this F ratio, this F quotient is going to get larger and larger, pushing us further to the right in the F distribution, meaning that it's going to be more likely that we're going to be able to reject the null hypothesis. However, removing individual differences is an advantage only when the treatment effects are reasonably consistent for all the participants. So what does this mean? Well, this means that if the actual effect of the independent variable or the treatment is not consistent, then the individual differences will tend to just disappear. And the value in the denominator is not noticeably reduced. So if our variance between groups is just still fairly minimal, if it's minimal because treatment effects are just not consistent across our three groups, then yes, we may lower our variance within groups, but it's still not really going to move the needle much in terms of our overall F ratio. So the F ratio for the repeated measures ANOVA has the same structure that we used in the independent measures ANOVA or the one-way ANOVA. The big difference, though, is that the individual differences are a part of the one-way between subjects ANOVA. The ANOVA F ratio, we eliminate those in the repeated measures F ratio. That's, again, because everyone in the various conditions are the same. So in the one-way ANOVA, we had two sources of variation, right? We had between groups and within groups. In a repeated measures ANOVA, we now have three sources of variation. We have between and within, but we also have what is known as the between persons. That is that component that is going to be made up of our individual differences. We are able to subtract this component, which is then going to be able to reduce that within group variability. So here in this nice little flow chart, again, we have all sources of variation that we have. In a one-way ANOVA that we covered in chapter 11, we can separate that into error and groups, right? Your between groups is your treatment effect. Your within groups is your error. But now we can actually divide that error, further partition it into within groups and between persons. This between persons variability is, again, that which we can take out of the error term because all of our participants are the same. So a new source of variation has appeared. We call this the between persons variation. So here's the between persons variation. And this is the source of variation associated with the differences between person means averaged across the groups. So how do we go ahead and solve for this? Well, we need to compute the average score for each person across the different conditions. So let's say that we had 4 people and we had 3 different groups. So person number 1 would give DV values or dependent variable values for each of the conditions. Person number 2, person number 3, person number 4. And what we're doing with the between person variation is we are going to look at the average DV values for each particular person. And any differences in participant characteristics across these multiple groups are equal because the same people are observed in every group. And because the measurements were obtained from the same groups of people, individual differences are constant across the trials, and we can then remove them from our error term. Now, as all of our parametric tests have shown, we do have assumptions. So we assume that the distribution of the dependent variable in the related groups should be approximately normally distributed. We say that the scores from different participants within each particular group or sample should be independent of one another, right? So in condition 1, you have all these different people giving a DV value. The assumption of independence says within the groups, person number one's value at time point one should not be influencing person number two's or person number three's or person number four's. Another assumption that we have that's specific to a repeated measures ANOVA is that is called sphericity. This refers to the variances of the differences between all of our different pairs of groups. So this is the condition where the variances of the differences between all of the different combinations of related groups are said to be equal. Now, this is similar to the homogeneity of variance assumption in our one-way between subjects ANOVA. Now, this is not necessarily something to stress about. If this is violated, corrections can be made. So those are inbuilt into different statistical packages where if you violate this assumption of sphericity, you can correct the degrees of freedom in your reporting. So we're not going to dive too much into that in this class, but it is something that I just want to at least make you aware of. Now, the hypotheses for the repeated measures ANOVA are exactly the same as those for the independent measures ANOVA. Our null hypothesis is always a statement of no difference. We're stating that for the general population, there are no mean differences among the different conditions, right? So it doesn't matter that there are three different groups, they're all equal. The alternative hypothesis states that there are mean differences, and really that some difference exists. We're not necessarily saying where that difference will be, but we are saying that there is some difference between the groups, or there is at least one mean that is different. If at least one mean differs, then that null hypothesis, for all intents and purposes, is wrong, right? Now, can we reject? That will be determined based on our data and our statistics. So when we're doing hypothesis testing, we have a few different steps. So in the first stage, we need to calculate our total variance and make sure that we partition that into our between treatments or our between groups and our error or our within. And then in the second stage, we begin with the variance within treatments and then measure and subtract out that between persons variance. When we do that, that is going to then lower our within treatment variance. The remaining variance we call our residual. That's what we'll use in the F ratio. That gives us a measure of how much variance is reasonable to expect after the treatment effects and individual differences have been removed. So the steps in solving for a repeated measures ANOVA, we calculate the sum of squares. So we're going to calculate our sums of squares total, our sums of squares between groups, and our sums of squares between persons. And with those three, we can then calculate the residual sum of squares. Now, we need to find each participant's average across the conditions. That's one of the key points in solving for the between persons variation. We calculate our degrees of freedom for total, between groups, between persons, and error. These three partitioned parts will add up to the total. And we are going to use the between groups and the error degrees of freedom when we are consulting our F table to find the critical F value based on our given alpha values. Then we finally build our ANOVA summary table. We obtain our specific F value, and we can then determine whether we can reject or retain the null. Now, how do we solve for degrees of freedom in a repeated measures ANOVA? The total degrees of freedom is solved as k times n minus 1. You can also write this really as capital N, because again, the number of groups, k, multiplied by the number of people in each group would give you the total number of cells that you're looking at. So we try to avoid using capital N here just because capital N means the total number of people. But in a repeated measures ANOVA for the total degrees of freedom, we're going to be interested in the total number of DV values that we have. That minus 1 will give us the total degrees of freedom. We can then split that total into 3 different parts, one for each source of variation, that being between groups, between persons, and error. Now, the degrees of freedom between groups is the same as the one-way ANOVA, just k minus 1. K is the number of levels of that independent variable or factor, so k minus 1. The degrees of freedom between persons is going to be lowercase n minus 1. That is the number of participants per group, minus 1. And the degrees of freedom for error will be these two degrees of freedom values multiplied by each other. Now, once you have these two and the total, you can use subtraction to find this last one, or you can solve for the degrees of freedom for error value by using this formula here. What you need to remember is that your total degrees of freedom, being broken down into three different parts, these three parts will always sum to give you the total degrees of freedom. So always just check and confirm that that is indeed the case. So how do we calculate sums of squares total? This is the this is the definitional formula. Now you can certainly use it if you would like, but I give you the computational formula so that you're not having to solve for grand averages. So the sums of squares total is we're summing up all of the squared deviations away from the total mean value. But we write this here computationally. The sum of x squared minus the sum of x's squared over n. In our between groups sums of squares, we are summing up our deviations from each group's mean minus the grand mean squared and multiplying that by the number in each particular level. Now, this is the definitional formula. We can rewrite this in our computational formula. The computational formula says that we're going to sum, that's sigma, everything in this bracket. Remember from our discussion with the one-way ANOVA, the sum of x sub k just means the sum of x's in that specific group. So if you have 3 levels, you're going to have 3 components. If you have 4 levels, you'll have 4 components. If you have 5 levels, you'll have 5 components to this. And then once you get this value here, you will need to subtract the sum of x's squared over n. Now the sums of squares between persons, again, this is unique. This is unique to the one-way repeated measures ANOVA. So this is where you're going to take the average for each person. This is the row average minus the grand or the total average squared. So you're going to sum up these squared deviations. And once you add this up, once you add this term up, you will then need to multiply that by k, or the number of groups. The reason why we're multiplying this by k is because, again, everyone is the same across the conditions. So we're accounting for the number of conditions in this calculation. The sums of squares for error is just taking our total sum of squares and subtracting our between groups and between person sums of squares, because sums of squares total is broken down into these 3 components: error, between persons, and between groups. These 3 must add together to give you the total. We then build our ANOVA summary table in the same way that we did before. Now, some statistics programs will remove the between persons and the between subjects line and put it as its own table. This is what Jamovi does. So in Jamovi summary tables, you'll see the between persons component as its own smaller table. You're still going to organize your table such that you have your source of variation, your sums of squares, degrees of freedom, mean square, also referred to as variance, and then your F ratio. And we are asking the question ultimately, is our F in the critical or rejection region? If it is, then we reject the null. If it is not, then we fail to reject. Remember that in our F distribution, this is a positively skewed distribution based on our specific alpha value, typically 0.05. Whatever this value is, we are going to call this the critical value. And we're going to compare our calculated value to this. If our value is greater, then we're going to reject. If it's less than, we fail to reject. This is why lowering that error variability, which puts our F value further out to the right, is so important. It adds that power. Now, effect size for repeated measures ANOVA, the most common method is to compute the percentage of variance that is explained by the treatment differences. We call this eta squared. So the formula for computing effect size for a repeated measures ANOVA is to take our sums of squares between groups or between treatments and divide by our total minus the between subjects. This is that between persons component. Another way to write this is to take your sums of squares between groups and divide by your between groups plus your error. Notice that we are not incorporating the between subjects component. Okay, so just keep that in mind when you're looking at effect size. Now, the interpretation is similar to how we solve for eta squared in the one-way ANOVA. So we say the certain percentage of variance in our dV can be explained by our IV. So ultimately, the purpose of our analysis being comparing dependent groups, our question is, what's the scale of measurement for our outcome variable or our dependent variable? If it is interval or ratio, meaning that we are working with continuous data or discrete data that is interval or ratio in nature, it's going to be dependent on whether we are working with 2 or 3 or more groups. If we only have 2 groups, like a pre versus a post design, time point 1 or time point 2, then we're going to use just a dependent samples t-test. If we have 3 or more groups, though, we are going to use the one-way within subjects ANOVA.